Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
So this problem we have here is mainly conceptual. So what we have is we have a sheet. So let's draw a sheet first. So it's just like a plane. We'll make it a little bit longer so we can see what's happening. So we have this sheet. It doesn't have to stop here. We could say it continues on to infinity, but I can't draw to infinity, so we'll represent it like that. And we take this sheet and we pick it up and we curl it. So what we end up having, so we take this point and touch it to this one, we'll end up with a big cylinder of radius r. So that's curling up this sheet. Now we're told, so this is a cylinder now, and we have this axis. I'll draw that in red. We have this axis of the cylinder. That goes down the middle of the cylinder. So this is a long sheet, and we're told that we have a magnetic field here running parallel to the axis. So that means that if our magnetic field is running in either direction here, so it would be in or out of the page, our magnetic field will be in a circle around this wire. So we have our magnetic field that travels all the way around, completes a circle. Now we want to show, or we want to find out what the magnetic field looks like outside of this cylinder. So we have Ampere's law that states that the sum of the magnetic fields that are parallel to the current, or not the current, sorry, parallel to a small change in length is equal to mu naught, the permeability of free space, times the current. So once again, we have to kind of figure out what the left-hand side of this equation is telling us. So we have our dl. If we take a small portion of our cylinder here and cut it into a dl, so this is our delta L. If we were to take this delta L and make it really, really small, it will appear as if it's straight, as if it's a straight line. Kind of like the surface of the Earth. We're so close to it that it looks like it's flat. So it looks, if we were to take this and shrink it down really, really small, it looks like we have a straight line here. In that case, the magnetic field will point, depending on which way our current is flowing, either to the right or to the left. So it is parallel at every point. If we split this up entirely all the way around into the same length dl, at every point the magnetic field is going to be parallel, which means our sum B parallel turns into just B. So we have this whole thing here just turns into the magnetic field, B. We don't have to worry about any summation. It's still the sum of the delta L's though, so now this part becomes a sum. because this sum encompasses everything on the left-hand side of the equation. This is the sum of the change in L, the delta L. And that's still equal to the same thing on the right-hand side. So we found out part of our left-hand side. So we need to figure out this part now. So what's the sum if we break this entire radius up into little sums of delta L? We add them all together. It gives us the entire length here, which is the length of our rectangle that we had here. So it'll give you this length. And we can calculate that with the radius. That's just equal to the circumference. So we have the sum of delta L is equal to the circumference of our outside of the cylinder, which is equal to 2 pi times the radius. That's a terrible pi. Let's try that again. 2 pi times the radius. So now we can substitute that into this equation. That turns the equation into B, the magnetic field, is equal to 2 pi times the radius. Is equal to mu naught times I. Mu naught times I. So what happens now if we're outside of the cylinder? If we go out to, say, a big R here. Well, the magnetic field will stay the same because we have no current out here. But if we make an Amperian loop all the way around this magnetic field, so we make it parallel to the magnetic field out at this point, key point being parallel, it'll be the same thing that happened before, except our R, little r, will now turn into a big R. So now out at the point here, outside of the cylinder, we have the same magnetic field because what's producing it is this current here. And we've drawn an Amperian loop around that. So our only source of magnetic field is coming from that wire still. So this is still the same B. I'm going to move the 2 outside here. And it's still the circumference, but we have a bigger circumference now. We're farther away from our center point here. This is where our axis starts, at the center of the cylinder. So now we have big R is our radius. Now we're out to this point. And it's still equal to the same current, because as with the magnetic field, we still have the same current, which is in the blue circle here. So it's still mu naught times the current. Now, if we want to solve for B, we can just move all this over to the other side. So for part A, we'll have B is equal to mu naught. Let's move down a little bit so we have some more space. Times I divided by everything else on the left-hand side. So 2 pi big R. And the only difference between R's is the little r is for the radius of the cylinder, big R is for your distance outside of the cylinder. So this is your part A. So now we need part B. What happens if we go inside the cylinder? What happens if we draw another Amperian loop here? So if we have another loop inside the cylinder, what current does this loop enclose? Which is the definition of Ampere's law. We have to enclose a current, but anywhere inside the cylinder here, so we are less than little r. anywhere inside the cylinder, we have no current, which means that by Ampere's law, our I is 0. Now you can kind of, to see this a little bit more intuitively, pretend you have a circle. We're inside this. All of the current is on the outside here. If you take a point here now, and draw a straight line, pretend it's straight, even if I can't draw straight. So this portion, so this part in red is the part of the wire on the other side that will contribute. It will be farther away, but we'll have more wire here that contributes to this little section on this side. And it will all cancel out. So you have charge on this side, and you have charge on this side, and they all end up canceling out. Because we're closer here with less area, but we're farther away with more area, and they perfectly cancel out. So everything inside of a conductor will have no magnetic field present. But we can prove it with Ampere's law by just stating that it encloses no current. Because we have no current inside of this. All the current is on the outside and flows parallel to this red axis here. So we enclose no current. So for part B, we have, let's do black. For part B, we have, that's a D. For part B, we have that I equals 0. No current is enclosed by the Amperian loop. Therefore, B equals 0. And that will solve it for you.